basically OH. We will see thiols, which are similar. They have a functional group of SH. We will see ethers, kind of a carbon, oxygen, carbon sort of functional group. We also see aldehydes, which have a carbon, oxygen, double bond, hydrogen as its functional group. And lastly, we will see ketones, which is a 3-carbon run with a carbon oxygen double bond in the middle here. So a lot of oxygen containing groups in this chapter here in terms of organic chemistry. So let us get started here. As I mentioned before, there are sort of our functional groups. Alcohols have the hydroxyl group. That OH group, again, which makes an alcohol. I think we saw this one last time. Our aromatic benzene with an OH group is phenol. Also something like methanol there. Again, our ether having the functional group basically carbon, oxygen, carbon. So this is an example one, basically carbon, oxygen, carbon is our functional group there. Thiols, as I mentioned, similar to alcohols, except for obviously sulfur, which is right below oxygen on the periodic table. So they do share similar type of functions as they go through it there. And again, we're going to talk about each of these as we go through them. So first off, we're going to start with alcohols. And when we talk about alcohols, we do name them, and they are named basically by taking that alkane name, dropping the E, and basically putting OL. So, for example, here, we have our methane, taking out one of those hydrogens and replacing it with that alcohol sort of functional group is now no longer methane. It becomes methanol, OL, like an alcohol basically at the end. As we talked about a number of times, pretty much again, those first 10 alkane names, it's pretty much what everything's sort of based off of in terms of how you name them. And alcohols and all these other ones are really no different. Sometimes a common name is used for this, where they will just kind of name the group that's attached to the OH like a alkyl group. And basically, as you can see here, that is a CH3, which is a methyl, and that is the common name, which is methyl alcohol or ethyl alcohol. If you have 2-carbon group attached to there, or ethanol. So sometimes you will see sort of a common name used with alcohols. We will go with, for us, really the IUPAC way of naming, which again is that more formal way of naming these guys. But again, like I said, sometimes that sort of common alkyl group naming is definitely used. Now, when we look at alcohols, as well as we'll talk about here, we can actually classify alcohols kind of the same way as we classify carbons as primary, secondary, or tertiary. And we can have, for example, a primary alcohol as kind of the same concept there. You're going to go to the carbon, but in this case, the carbon does need to have the OH group attached to it. So obviously here, that carbon has the OH group attached to it, and attached directly to that carbon is one other carbon. And again, that's what makes this a primary alcohol. You could also have a secondary alcohol, and much like sort of the carbon that we talked about previously, you would actually have, and I'll just do it this way maybe. This again is our carbon that has the OH group attached to it, and directly attached to that guy, as you can hopefully see, is 1 carbon and 2 carbons. So this would be a secondary alcohol in this particular case. And we could also have a tertiary alcohol, which just like a tertiary carbon, will find 3 carbons attached directly, again, in this case, to the carbon that is attached to the OH group. So again, here we have 1 carbon attached directly to that carbon, 2 carbons, and 3 carbons, giving us a tertiary alcohol. And as we will see, as we sort of talk about some reactions that they undergo, depending on whether you're dealing with a primary alcohol, a secondary alcohol, or a tertiary alcohol, you may actually get some different products formed in certain reactions that occur. Any questions on how to identify that? So really the same way as you identify carbons. Again, here you're just looking at the carbon that has the OH group attached to it, and that's the one then you want to see how many are attached to that one. Now, when we do name alcohols, there are a couple other things that we also do with them. First off, we are always, again, still looking for the longest continuous carbon chain. In this case, it would need to contain the OH group as part of that chain. We are also going to give the numbering of the chain priority to the OH group. So the OH group here is important. We want to give the OH group the smallest number when we're numbering the chain, kind of like what we do with double bonds and triple bonds. We want to give those guys the smallest number. So here with the OH, we want to give it the smallest number. Also, just like double bonds and triple bonds, when there is sort of more than one place where the OH group can be attached, you also need to give the number of where it's located. So we would need to give number. For alcohols, that's approximately about 3 or more carbons is where you got to start sort of giving numbers of where the OH group is attached. Obviously here in the one we got up here, which is methanol, there's only 1 carbon, so it cannot be anywhere else, so you don't need a number. Even with ethanol, you don't need a number because it's either on this carbon on the left, which would be number 1, or it's on the other one on the right, which would be number 1, so you don't really need a number. So about 3 or more carbons, you do need to give those numbers. So if we take a look here, once again, we're going to look for the longest carbon chain. Looks like maybe 1, 2, 3, 4, 5, 6 straight across. We could also go 1, 2, 3, 4, 5, 6 going up. So it looks like 6 is a winner no matter which way you go. So we will go with maybe just the straightest 6 there, and we'll go just straight across here. So 6 carbons that obviously has the OH group as part of it is going to be based off of hexane. Because this is, again, an alcohol, it will become hexanol, OL. And once again here, in terms of numbering, we do want to give the OH the smallest number. So you could probably see that if you go right to left here, that is going to give that OH the smallest number. And then this would now become 2-hexanol. Again, the 2 is where the OH group is located. And once you sort of lock in your numbering, obviously for the OH, anything else that is there, you will then name like normal. So here we have a methyl group. And since it is at carbon number 5, this would then be 5-methyl 2-hexanol. Yeah. Any questions on that one there? So I would say very similar to alkenes and alkynes in terms of having to give the number of the OH group like we do with the double bonds and triple bonds. And again, that locks in your priority. Now, just like normal, if it is kind of a tie in terms of the OH, no matter which way you go, then you would probably go to groups that are there and alphabetical and try to give those groups the smaller number would be the next sort of important thing if you come to a tie. All right, so why don't you give these a name, and let me see, let's do why don't you also draw pentanol. So once you draw 3-ethyl 2-pentanol, once you also roll cyclohexanol as well. I think on the first one here, no matter which way you go, I think 5 is going to be a winner. You get 5 straight across. Obviously, that contains the OH. You could also get 5 if you kind of went up that way as well. So 5 with an OH group tells us it's an alcohol. So clearly that's going to now become pentanol, OL. We do definitely, because it's 3 or more carbons here with an alcohol, need to give the location of the OH, and we want to give it the smallest. So again, just looking at it, hopefully you could be able to see that going right to left is going to give it the smaller number. Obviously, if you went the other way, you're looking at like a 4 for the OH, and obviously that's larger. So that's going to now become 2 pentanol. And here at carbon number 4, there is a methyl group. So that will be 4-methyl 2-pentanol. Questions on that name there? Taking a look at the next one here, we got this entire aromatic benzene ring that has an OH on it. So that entire thing, again, has a special name, as we talked about last time, as we saw here at the beginning. That is phenol. And again, that's basically a benzene ring with an OH group on it. Because that functional group OH, we don't really need to give the number in the name, but in terms of other groups, that definitely will be carbon number 1. And because this is benzene, it doesn't really matter. You don't have to worry about kind of which way to go in terms of numbering. You could actually just go whichever way is the smallest, because there are 3 double bonds in there. So you'll always be going through a double bond no matter which way you go. So smallest number there to the bromine would be go this way, and that would give us 3-bromol phenol. Any questions on that one there? Lastly here, longest carbon chain, let's just straight across, I think. So we got 1, 2, 3, 4, 5, 6, 7, and 8. Again, that obviously has the OH group attached to it. And 8 is based off of octane. And obviously here, that's now going to become octanol OL because we have the alcohol group there. And again, just looking at it, you hopefully should see left to right here will give that OH the smaller number. And that is now going to be 3-octanol as the location of the OH group. And that would then put our bromine there at carbon number 5. So that would be 5-bromol 3-octanol. Questions on that particular one there? All right, so when we're drawing structures, just like we always do, we just kind of want to work our way backwards in the name, and that is pentanol. So obviously the pentane part, if you will, tells us it's 5 carbons. The OL at the end tells us it's an alcohol, right? So that's what we're going to start with. We'll just start with our 5 carbons. 1, 2, 3, 4, and we'll go 5. OL tells us an alcohol, and the 2 tells us again where the OH group is attached. And as we talked about previously, since you're drawing it, you could go kind of left to right or right to left. I'm going to call this guy right here my carbon number 1, which means my 2 would have the OH there. That's going to take care of pretty much that part of it. Because I did lock in my numbering going left to right here, I have to keep that for this group as well. So a carbon number 3, in my case, should be a ethyl group, which is a 2-carbon group. And again, you could either put the hydrogens now or later. So you could go CH2, CH3. At this point, we are out of name. And like normal, we're just going to add enough hydrogens to get carbon to 4 bonds. So guy at the end here going to go with 3. We need 2 there, only 1 there. Also only 1 here and 3. And that obviously would be a condensed structure. If you want to do line structure, you really would do the same thing. You just go with 5. So 1, 2, 3, 4, and 5. And again, at carbon number 2, we would put our OH. Remember here, you do need to write the OH because if you don't write it, it's not an OH group, right? It's a methyl group, right? So you do have to specify it. And at carbon number 3 would be our ethyl. So something like that would be our line structure. Any questions on either of those there? All right, same thing here. I see hexanol. So OL tells me it's an alcohol. Hexane tells me is 6, but I also keep going and I also see cyclo. So that tells me it's a ring of 6, right? So it's a ring type structure. And that is cyclohexane. Remember, cyclohexane does not have double bonds, right? Benzene has the double bonds, or cyclohexene will have a double bond. In this case, really, it's your call wherever you want to lay up that OH group. So I'll just go straight up on top. And because I did do that on top, that would be obviously my carbon number 1. And also you have a choice here. You could go left or right. So I'll go right. We'll just go 2 and 3, and you could put a chlorine there. And obviously, if you want chlorine on the other side, it's perfectly fine as well. Actually, it's just the same thing, just turned around, basically, in that case. This would be more obviously of a line structure, which is typically what we do for our kind of cycloalkanes and stuff. But if you wanted to condense, you'd just do kind of the same deal, and just kind of put in your 6 carbons, and then obviously here we actually only have 1, and down here we have a Cl, which would also have 1 hydrogen. These guys would have 2s around there, and there you go. And you can just do a condensed, something like that. Any questions on naming or drawing alcohols? So again, very similar to double bonds, triple bonds. OH gets the priority, and everybody gets numbered accordingly. Any questions on that there? Okay. All right, so as we've been talked about here, alcohols, ethanol, which is also again commonly called sometimes ethyl alcohol, again can be made through fermentation of glucose. Is the alcohol of alcohols, if you will. Yes. Good stuff, I suppose. Also, some other alcohols here: glycerol, 1, 2, 3, propane triol. Actually has 3 OH groups in it, and it is very, very polar because of that. Each of those OH groups also makes it very sort of soluble in water. And alcohols also can be soluble in water because of the presence of that OH group. So that OH group is a polar group. So these alcohols do have a polar group, which because of that does allow it to work well with water in certain situations, because water pretty much has the exact same group in it, negative and positive, and they could do some hydrogen bonding, for example, with water. So some alcohols are fairly soluble in water. They will mix really well with water because they can interact well with it through hydrogen bonding. And an increase in the number of alcohol functional groups also does increase things solubility in water because it gives it a lot more locations where they can interact. Ethylene glycol is basically antifreeze, right? And it also has some alcohol groups there. And it has a good property. It actually can increase the boiling point of water in your radiator so you don't overheat, and also can lower the freezing point so it doesn't freeze if you're in a really cold temperature. So it actually has a interesting property when you add it to something like water. BPA, some plastic here. Again, you see our alcohol sort of groups there on it. So let's talk a little bit about some reactions that lead us to alcohols and alcohols undergo. We actually talked about in the previous chapter how we make an alcohol. So a reminder that we can make an alcohol through an addition reaction of an alkene. So if you have an alkene, and you add water to it, do a hydration reaction, which is again HOH, it is going to add across the double bond here. And when it adds across the double bond, just like we talked about, you do need to make room for it. So basically, again, our double bond becomes a single bond. And we will get a alcohol that is made here. OH to one and H to the other. And that's how we form alcohols, is through this addition reaction we talked about in the previous chapter of alkenes. Remember as well, though, if there is a difference in the number of hydrogens on that double bond, the one with the most hydrogens will get the hydrogen when the H is added from the water, and the other one will get the OH when it does so. So in this case, we go from ethene to ethanol here. And again, we produce a primary alcohol as a result of this reaction. So we can obviously produce alcohols through this hydration reaction. We could also basically do the opposite reaction. And the opposite reaction is a dehydration reaction. And dehydration basically means we take out the water that we put in. So hydration, we put the water in, we get an alcohol, we want to get rid of it. We basically heat it up with a little bit of acid, and it will basically take the water off of there. And just like when we put the water on, we have to get rid of the double bond. When we take the water off, we just put the double bond back on, basically. So it's really the exact opposite in a sense. So here, if you do this, you start with an alcohol, you heat it up. It is going to take water out. And just like we put it on, again, the water doesn't come from the same carbon. So we get an OH from one carbon and we get the H from the other carbon. So just like it goes on is how we take it off. So you have to take it off from each of those guys. These two guys will come off as water. And when we do that, if you were just to draw it again without that on there, you could see that the carbons in the middle are short a bond, basically. And again, that is why we're going to then kind of put our double bond back on. So pop a little double bond right back on there, and we get our alkene back. So a dehydration reaction is essentially the opposite of the hydration reaction we saw in the previous chapter, where we make an alcohol and you take it off. Now, there could potentially be a difference in the number of hydrogens when you do that. In this particular case, there really was only one oxygen, right, that we can take, or sorry, one carbon that we can take the hydrogen off of, since the other one had the OH. So it is possible that you could have a situation. Let me start somewhere to draw maybe here. There, I'll go here. So let's just say we had here in the middle, maybe. We'll do. So maybe we'll just do. That's right. So let's just say we were going to dehydrate this guy with a little H plus. And again, that's just a abbreviation for an acid being used as a catalyst. Again, a catalyst is just there to kind of speed up the reaction. It's not really per se a reactant or a product, and some heat, right? So clearly here, we're going to take out our OH, right? But in this case, we actually have two possible spots that we can actually take the hydrogen from. We could take the hydrogen from the guy on the left. So if I took the hydrogen here as like maybe my first option, I would end up with this. And again, everything's going to be exactly the same, except obviously I'm just taking the water out. And obviously where I took the water out, I then need to put my double bond back in. And I feel like I was missing a hydrogen there to begin with. So we pop a hydrogen there. That would be good. There we go. Now I put my double bond back in. And that would give me one option, right? The other option would be to, maybe I'll just box these in red, take my OH and take a hydrogen off of obviously the guy to the right there would be my other option. And that would give me, if I just drew it, here, I think. And again, nothing's going to change other than I'm going to take off the water that I boxed now in red. I'll forget my hydrogen there. And then obviously I'm going to put my double bond back in over here. And these would give me my two possible options in this case. So there is actually a rule, as you could probably imagine, that we follow to give us kind of a major product and a minor product. So if you remember that when we put the hydrogen on, it goes to the carbon that had the most hydrogens to begin with. When we actually take the hydrogen off, we actually take it off from the least hydrogens. So we want to go from the least hydrogens if there is a difference when we remove H to make water. So in this case, it actually would be this guy here that would have the least number of hydrogens. This guy has 2 hydrogens directly attached to it. Obviously, this one has 3 hydrogens that are directly attached to it. And if we did that, that would give us our first one here. This would be our major product. This would be our minor product. And again, usually you want to kind of go for that major product. Now, again, this is only a situation where there is a difference. If both of those, again, carbons on the right and left had the same number of hydrogens, just choose either one. It doesn't matter. You'll end up with the same thing. So it's only if there is a difference. So putting the hydrogen on to the most, when you have to remove it in a dehydration reaction, you take it from the least. If there is a difference, no difference, grab it from whichever one you like, and you'll be fine. Any questions on that there? All right, so hydration makes an alcohol, dehydration takes it away. Let's then talk about really some main types of reactions that alcohols undergo, and these are oxidation and reduction reactions. And we talked about oxidation and reduction reactions earlier on when we were talking about types of reactions. And remember that when we talk about oxidation, the earlier sort of version of it that we saw the most was something loses electrons, and reduction is something that gains electrons. And when we're in organic chemistry here, we really don't look at those definitions. We actually use the other sort of major definitions of oxidation and reduction. So oxidation, as it says there, the other sort of definitions is something will gain oxygen from the reactant side to the product side. So somebody gains oxygen, reactant side to product side is an oxidation. It could also lose hydrogen as it goes from reactants to products. So something loses some hydrogen along the way, that is a classic oxidation sort of step. Reduction is kind of the opposite of those two definitions. It is something that can lose oxygen as you go from reactants to products, or gain hydrogen as you go from reactants to products. So these are really kind of the two definitions that we see in organic chemistry for oxidation and reduction. We really don't see too much of the electron sort of definition when we're dealing with these. And this is because we are dealing with a lot of non-metal and non-metals, pretty much all non-metals for the most part. And we really don't get those transfer electrons because everybody's sharing electrons. So we really look at sort of the oxygen or hydrogen either appearing or disappearing. Any questions on that there? All right, so let's take a look here at the first type of reaction, and that is with a primary alcohol. So remember again that this is a primary alcohol because the carbon that is attached to the OH is attached to one other carbon, which makes it a primary carbon. So this oxidation of a primary alcohol will result in an oxidation to occur. And the definition that we're going to see here, actually, I'm going to do it this way, I think. Draw out that bond so it might be easier to see. So we have an OH bond up there, and we got our H's. So what's going to happen in this case is we're going to go through oxidation, and sometimes oxidation is actually just kind of abbreviated with a little O and a like box there, or some parentheses there, or brackets, I guess. And that means oxidation. So the definition of oxidation here is we're going to lose H2. So where do we lose H2? We actually lose H2 100% of the time, always happens right here at the carbon-oxygen bond. So right here is always where you're going to remove your H2 from, that carbon-oxygen bond. Always for sure, you're going to grab the hydrogen that's attached to the oxygen. Now, for the other hydrogen, you could choose either of those two that are attached to the carbon. So it doesn't matter which one you choose. You could choose either two. I'm just going to choose the bottom one here. And those two that are in green, I'll put it right here in green, is obviously going to be our H2 that we're going to lose. And that is what is causing it to go through oxidation. So that H2 will come off. Once again, as we talked about last time, when you're drawing these sort of products, you pretty much have 99% of the picture done for you. I should not even think too much about what I need to draw other than I should just copy what's there. The only thing I should take out are the two hydrogens that are in green. Yeah, so everything else stays exactly the same. Don't get creative on it. It doesn't go weirdly. So I'm just going to draw everything exactly the same. The only thing I'm going to take out is the two hydrogens that were in green. So this reaction you could kind of think of as kind of similar to like what happens when we make a double bond or we make a triple bond, right? If I want to make an extra bond between two carbons, what ends up happening? I have to remove two hydrogens, right? One from each. And the same thing happens here. I remove two hydrogens, not from two carbons, but from a carbon oxygen. And that is going to now become double bonded. So we're just going to slap a double bond between the carbon and the oxygen. And we'll slap a carbon and the oxygen. That way everybody meets the octet rule. I would say sometimes people don't draw it all that much here, but there are the non-bonding electrons still on the oxygen up there like normal. And we put a double bond in here. So in a oxidation of a primary alcohol, you remove two hydrogens, one from the O and one from the carbon that's attached to the O, and you double bond between the carbon and the oxygen, and you are good. You're done at that point. We go from an alcohol in this case, which is ethanol, to this guy, which has a functional group right about there. That is the carbon, oxygen, hydrogen functional group there. That is an aldehyde. So we go from an alcohol to an aldehyde. And this guy, by the way, just so you know, is known as ethanal, AL, also based off of ethane. And we actually name aldehydes with an AL at the end of the name. Very simple. Any questions on that there? So this is the oxidation reaction. What would happen if I go the other way? That's the reduction reaction, right? If I throw the reduction, I throw the hydrogen back on, and that is the reduction reaction. If we go the other way, that is basically your reduction reaction, put the hydrogen back on. And that's also very similar to sort of when we put hydrogen plus a carbon-carbon double bond. We basically make the carbon-carbon double bond into a single bond, and each of those guys get a hydrogen. So if you were going in the reverse direction, you would break the double bond between the carbon and oxygen and just put a hydrogen on each, and you're good to go on the opposite direction. Any questions on that there? So just to show you that if we, again, we went this way here. again, our aldehyde from our primary alcohol. But if we were going to go the other way and do the reduction, we would be starting with our aldehyde and we'd be adding H2. And again, the only thing that changes is that carbonyl carbon, which is this guy right here. We're just going to make it a single bond to give room for the hydrogens to come in. Everything drawn the exact same way. Just copy exactly what's there. So you have an H, a C, an H, an H, a C. Going to make this now a single bond and an H. And now we have room for those two hydrogens coming in. Just like to do with a double bonded carbon, they don't go to the same carbon. One goes to the O and one goes to the H. And that is the reverse reaction, which is the reduction reaction. So oxidation going in the top direction, reverse it by doing the reduction reaction. Basically just break that double bond, single bond, H to each, and you get your alcohol back. You then go from a aldehyde to a alcohol. Yeah. Any questions on that? Now, with a primary alcohol, it will get oxidized to an aldehyde. But in this case, if we take our aldehyde that we made, it can also get oxidized one more time. So a primary alcohol can get to an aldehyde. And if you want to keep going, you could actually oxidize the aldehyde one more time. But this oxidation is not adding hydrogen. This oxidation is actually going to be adding the other definition of oxidation, which is we're just going to pop an oxygen in there, basically. So we're going to add an oxygen if you continue on. And where does the oxygen go? Well, frankly, doesn't happen this simple, but it ends up right there, basically, right with the O, and we make an OH at the end. And we end up with, again, the exact same thing, except we're going to insert, I'll make it blue here, an oxygen there. So it goes through oxidation, and we will have an H with it still. And we will make this guy here. And this is a functional group as well. This is a carboxylic acid. So you could actually take a primary alcohol and oxidize it to an aldehyde. You could then oxidize that aldehyde to a carboxylic acid. And by the way, if you go backwards, that would be the reduction, which would take you back to the aldehyde and then back, obviously, all the way to the alcohol. So in the reaction of a primary alcohol, it actually can go a couple of steps to the end. One oxidation gets you the aldehyde, second one gets you to the carboxylic acid, which is another functional group here in organic chemistry. Question fell out there. Why don't you try one? Let's say we had all right. So what will you get if you oxidize this guy just once? Is just where the functional group is. That's really the only part of the molecule that changes. Everything else stays the same. So again, don't get super creative with it. Yeah. So that's really the only part that probably is going to change here. And that's really the only thing I should worry about. So what I know is an oxidation. This is a primary alcohol. And again, it's a primary alcohol because that carbon is attached to one other carbon. By the way, the name of this guy would be 1, 2, 3, 4, 5. So this is 1-pentanol, right? Is the name of this guy, as there's 5 carbons. And it's going through an oxidation. And remember that when we take a primary alcohol through an oxidation, out goes two hydrogens. And again, our two hydrogens are always going to come from that functional group, one always from the oxygen and one from the hydrogen there. So those are the two I'm going to take out. And I'm just going to draw it below. So our A product here would be essentially the exact same thing. I'm not going to change a thing other than I am going to take out those two hydrogens that are in green. And again, that's going to leave me here also some H2 that comes off. That's going to leave me a carbon-oxygen bond that I know that I then need to put a double bond in there, right? And that's going to give me my aldehyde, right? So just like normal, we remove two hydrogens between two things. You got to put a bond basically in there to make up the difference. Any questions on that one there? By the way, this guy is also 1, 2, 3, 4, 5 carbons. That is pentanal, Al. Yeah, that's the name of that. You don't need a number actually on that. Now for B, we're going to go one more oxidation step on this deal. And in this oxidation step on this primary alcohol, again, is we're going to insert an oxygen right there. It's just going to kind of insert an oxygen right in that spot. So once again, nothing else is going to change. So everything looks exactly the same. So you can pretty much just copy what was written there. Nothing else is going to change, except now we're going to insert our oxygen, and we still have the actually it's red, huh? We still have the hydrogen there if I get to it. There it is. And we still have that hydrogen there as well. Again, making our carboxylic acid. In case you're curious, we will get there. Pentanoic acid is what that is called. OIC. Yeah. Yeah, so it's a very long process, but that you don't have to worry about, obviously. But it happens. So on a primary alcohol, on really any alcohol, primary or secondary, when it goes through the first oxidation, we're always going to be removing the hydrogens. After you do like the first one, if you continue to oxidize that product, then you're going to actually be inserting oxygen in there. So it's always kind of the second oxidation that occurs. Or if you're just starting with an aldehyde, which is really the product of the first oxidation, it will be the oxygen you'll have there. Correct. So this question could be asked kind of two ways. It could be asked eventually, like we just did here, like you start out with a primary alcohol. First oxidation should take you to that aldehyde. Second one should take you to the carboxylic acid where you add the oxygen. Or since we're going to talk about aldehydes by themselves as well, if you're starting with an aldehyde and you oxidize it, it will oxidize to a carboxylic acid, and that's just the oxygen. There's a lot of process that happens that obviously we don't need to get into in this class. We don't get into this class, but it involves some acid and waters, and that's sort of eventually a water kind of attaches there, and that's sort of where the oxygen comes from, and then some of the hydrogens go off of it, and that's sort of how it eventually the oxygen works its way in there in the process. Yeah. Other questions? Yeah. Yeah. I'll be honest with you, any type of reaction, regardless of its oxidation, reduction, and like the hydration reactions we did the other day, the hydrogenation addition reactions, everything always occurs where the functional group's located. Yeah. And definitely with these, the first oxidation is always at that OH group is part of it in that carbon. So functional groups is always where sort of everything happens. And it's a really good thing to sort of keep in your mind, like I've been saying, and I make jokes like, don't get too creative with it because sometimes people see it and they think like all these weird things need to happen, like things need to break apart and other things form and stuff like that. But a lot of these are just basically the same thing you started with. Just one little small part around that functional group is what changes. And it's a good thing to keep in mind as you're sort of drawing those. Other questions? Yeah. All right, so there's our primary acid. And as we just talked about there, Aldehydes, again, can further oxidize to a carboxylic acid. And like I mentioned before, that's really just an insertion of an oxygen in that particular case. Now let's talk about secondary alcohols and what happens with them. They also will oxidize, and they will oxidize in a similar fashion. So we'll take this guy here, and we'll just take a look at it here. So that was like 2-propanol. So let's take a look at this guy here. I'm gonna put the right number of hydrogens in. That'd be good. I go that way and that way. All right, so this is going to go through an oxidation reaction. This is a secondary alcohol. And this is a secondary alcohol because, again, when we look at the carbon that is attached to the OH, that guy is, again, directly attached to two other carbons, right? So that's what makes it a secondary alcohol in this case, is those two carbons that are attached to the carbon that has the OH. The good news here is this is, again, a oxidation of an alcohol. So you could just remember, if I'm starting with an alcohol, I'm going through an oxidation. That is I'm going to take my two hydrogens off. So just like previously, the hydrogens will come off the exact same way. So we're going to take a hydrogen off of the oxygen here. So we'll definitely take this hydrogen, and we will take the hydrogen that is attached to the carbon. So just like we did in the previous one, those are the two hydrogens that basically go away. As I mentioned before, nothing else here is going to change. So this right here gonna be just like so. And obviously here we would get some H2 that would come off, and that came off from our kind of bluish hydrogens that we removed there. And just like we did before, the one thing that we now need to go back and put in, once again, always between the carbon and the oxygen here, is our double bond. So we're going to double bond that up. And we go from a secondary alcohol here to our friend, which is known as a ketone. And a ketone has a functional group of 3 carbons in a row with the carbon-oxygen double bond in the middle. By the way, the carbon-oxygen double bond is known as a carbonyl carbon. And it is actually, by the way, a polar group. The oxygen is more negative and the carbon is more positive in that bond. But that is always what we make here. So that is a ketone, and that is the functional group right about here. If you look at it, 3 carbons in a row and a double bonded oxygen in the middle of those 3 carbons. By the way, if I want to name the first guy here, what is the name of the first one? First alcohol there is called? Longest carbon chain is on this guy. 3 carbons, yes. So that is propanol. Do I need a number? I do need a number here. Is 3 or more. So this is 2-propanol, also known as isopropyl alcohol, also known as rubbing alcohol. Yeah, so that is all the same thing right there. Isopropyl, if you remember, is this group here, CH3, CH, CH3. That entire thing is the isopropyl group there. Maybe not the best choice of color there. I'll get rid of it. There you go. All right, so we go from there. And again, we go to a ketone, which this one, by the way, is 3 carbons. Ketones end in ONE. Dare I call this propanone? Yeah, ONE, just like a ketone. Yeah, so propanone, ONE is the name of what we formed over there here. So a secondary alcohol will oxidize to a ketone. Unlike your primary alcohol, it is not going any further. So this is it. It will not go on and make anything else. So just that primary alcohol will continue to oxidize that aldehyde this is going to be your dead end, if you will. Yeah, so that is the oxidation reaction. As we've been talking about, the reverse of that is the reduction reaction. So if you were starting with the ketone. So if you were starting with that exact ketone there, you would be reducing it, which means you would be adding the H2. And once again, the only place that's affected is the carbon-oxygen double bond. And just like when we have a carbon-carbon double bond and we add hydrogen, we need to make it a single bond. Same thing happens here if you're doing the reduction reaction and you're actually starting with the ketone. You would make that into a single bond, draw it exactly the same, except turn that guy into a single bonded. And in and in. And now each of those hydrogens have a place to land because we made room for it. Make them bluish. And we can put our hydrogen on the oxygen, just like when we take them off and we put our hydrogen back on to there. And this would be obviously the reverse of the oxidation reaction. This is the reduction reaction. And this is going from a ketone back to a secondary alcohol. Questions on those reactions there? Yeah. Correct. Yeah. In this aspect, so you can see here, it's also important, as we were talking about earlier, to know what type of alcohol you're starting with, because if you're starting with a primary alcohol and you oxidize it, you should end up with an aldehyde, not a ketone. If you start with a secondary alcohol and oxidize it, you should end up with a ketone and not an aldehyde. And if you want to get yourself to a carboxylic acid, you best be starting with a primary alcohol to take it to an aldehyde, to take it to a carboxylic acid. Yeah. Other question? Let's see, there's our secondary there. Now let's talk about our tertiary alcohol. So if we had a tertiary alcohol, try to draw it right here. We'll do this. We'll do it like this, I think. Let's draw it this way. All right, and here's our tertiary alcohol. And once again, it is a tertiary alcohol because if we look at our carbon that is attached to OH, that carbon is directly attached to 3 other carbons. Carbon number 1 there, number 2, and number 3, going to make it a tertiary alcohol in this case. So if we want to go through our oxidation reaction here with a tertiary alcohol, we know that we are going to take away H2, and we know from what we've been doing that we definitely are going to help ourselves here to the hydrogen that's attached to the oxygen. And now the hydrogen that comes off next should be attached to what thing? Should be attached to the carbon. Is there a hydrogen on that carbon? There is not a hydrogen on that carbon. So because it's lacking that second hydrogen that is needed to be removed, you get nothing. It does not go through oxidation. So a tertiary alcohol will not oxidize. You'll get no reaction because it's missing that second hydrogen on the carbon. That's obviously the carbon that is attached to the OH group. So you can't remove 2 hydrogens if you're kind of missing one. So a tertiary alcohol will not go through oxidation. So again, the importance of when you look at an alcohol, not just to go alcohol, right? You have to identify, I would start off with what type of alcohol it is. If it's a primary, it can get you to an aldehyde, can get you to a carboxylic acid. If it's a secondary, it can get you to a ketone. If it's a tertiary, it's not going to get you very far in terms of oxidation reactions. So it will not go through oxidation because it's missing that. Question on that there. All right, so you're doing, so remember, definitely we got some alcohols. It's important maybe to identify what type of alcohol you're starting with. because if you do and you know it's going through oxidation, you actually should know kind of what you should get, right? Before you even try to draw it. So that's kind of helpful. So we'll start with the alcohol. I'll save this one for the end since I had it at the end. I'm just gonna count some carbons here. That's carbon, right? 1, 2, 3, 4, and 5 carbons, right? So by the way, the name of that would be it would be pentanol, but it should be 1 pentanol. We would need to give it, right? So this is 1 pentanol. And is this a primary, secondary, tertiary carbon? This is it is a primary carbon. This little dot here is a carbon, right? And it's attached to that dot, which is another carbon. So that carbon that has the OH group attached to it, it's attached to one other carbon, which makes this a primary alcohol, which if we're going to take it through oxidation, which is what that means, I know I should actually end up with a aldehyde, right? Because we're just going to oxidize it here once. That means really everything else stays the same. We are going to take away 2 hydrogens. So if it's easier for you, you can maybe put in over here if you want, just to kind of see. Start with the eraser, try not to erase the entire thing there. Let's get rid of my name too, I think. Oh. So really this guy right here is a carbon, and it has 1 and 2 hydrogens right off of it. So now we can see hopefully our hydrogens that we need to remove and our other hydrogen. So just like normal, we are going to take away always the hydrogen that's attached to the oxygen, and your choice on this, one of these hydrogens that are attached to that carbon. So those are our 2 hydrogens that are going to come off over here. And, probably a good idea just keep track of everything. You can put the H2 over here. It's not really obviously the main product here, but it is kind of removed there. Now, everything else is going to be same. We're just going to draw it pretty much without those 2 hydrogens. So we'll go 1, 2, 3, 4, 5. We will go up to the oxygen. And if you want, you could still obviously leave the hydrogen if you want to kind of show it. What else do I need to do at this point? I need to make a double bond here, right? And that's going to give us our aldehyde here in line structure formula. If I didn't lose carbons, I should still have my 5 carbons there. 1, 2, 3, 4, and that would be 5 right there. And this will make our aldehyde, which again is pentanal. Al is the name of it. Any questions on that there? Yeah. If we oxidize it one more time, what would happen? Carboxylic acid, which means the only thing that will change is I'm just going to insert a oxygen at this point there, right? If we did take it one more time through the oxidation. Any questions on that one there? All right, take a look at the next one here. Obviously an alcohol. What type of alcohol is this one? This is a secondary alcohol. This carbon that has the OH group attached to it is attached to 1 carbon there and 1 carbon there, making this a secondary alcohol, which means if I oxidize a secondary alcohol, I should end up with our friend, the ketone, right? So again, just looking at that before you start drawing it could help kind of focus you on what you should end up with. For fun's sake here, since we're all doing alcohols as well, the name of this one would be, longest carbon chain is, I know 5 seems to be a winning number here today with me. So 5 is pentanol. Do I need a number? It is 2 coming in this direction, 2 pentanol. Is there anything else there? There's a chlorine hanging out, right? So that's 2, 3, and 4. So this is, we'll go above it, 4 chloral 2 pentanol, right? So now that we identify as a secondary alcohol, we know it's going through oxidation. So still going to lose our hydrogens, right? When we oxidize an alcohol. And just like any sort of oxidation of an alcohol, definitely taking the hydrogen there from the oxygen. And remember that we are not taking hydrogens from the sides. We are taking it from the same carbon that's attached to it. And we're going to take that guy. At this point, pretty much just draw everything other than the green guys, right? So we'll draw that in there. Maybe I'll go a little underneath here. So we'll go here. Still have the Cl. Still have those guys. Um, we got just an oxygen there, and still have this guy here. And now between the carbon and the oxygen, we're gonna double bond it up, right? And now we have our ketone in this case, which in this case is 1, 2, 3, 4, 5. This is actually known as 2-pentanone, and we'll talk about that in a sec. You can probably imagine what the 2 means. It's where the carbon-oxygen double bond is located in this case. And obviously here, this will not oxidize any further, so that's sort of your end product that you would get in this case. Any questions on that one there? Alcohol over here on the next one is a primary, secondary, tertiary. This one is a secondary, actually. So this is the carbon, right? That is attached to the OH, and directly attached to that is a circle now. What was a C a minute ago? A carbon there and a carbon there, right? So those are 2 carbons. So this is a secondary alcohol known as cyclohexanol. Right? So cyclohexanol. So secondary alcohol, just like above, should end up as a ketone. So again, not usually drawn in, but there is a hydrogen hanging out there on that carbon. And once again, we're going to take the hydrogen there and the hydrogen that is there. Everything else stays the same. Again, nothing funky happens, like it opens up. And we're going to then put a double bond right about there. Probably guessed the name, but this is cyclohexanone. O-N-E. Yeah, so cyclohexanone is the name here for our ketone. Kind of missed the carbon there on the double bond, but it's close enough. Question on that one there. All right, last one here. Alcohol on the bottom there. What type? This one is a tertiary alcohol. And again, is a carbon here attached to 1 carbon, 2 carbons, and 3 carbons. And when we oxidize a tertiary alcohol, we get no reaction. Yeah, so that was an easy one to draw. Not much to draw there, right? Any questions on any of those oxidation reactions? All right, top one here. Maybe I'll go here and do it. 2, 3, actually 3 more than 5. 1, 2, 3, 4, 5, 6, 7. All right, so we had, I think I was here, if I'm not mistaken. Yep. And we're gonna do this, right? So in this case, we're not starting with alcohol. This is actually a ketone, yeah, and that is your carbon, 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 3 carbons in a row with the double bonded oxygen in the middle. So that's your functional group right there. So it's a ketone. I'm adding hydrogen, not removing it. When I remove hydrogen, that's an oxidation. When I add it, it is a, yeah, so this is the reduction, right? So it's the opposite that's happening here. And this is basically, again, as we talked about, the exact same idea as adding again that hydrogen to our double bond. We need to make it a single bond and add those hydrogens in. So when we look at our ketone, the only place we got a double bond is between the carbon and the oxygen. So once again, that is the only thing that's going to change, is right here. And it's going to change the exact same way it does here. We just need to make it a single bond to leave room for those hydrogens to come in. And that means I'm just going to draw it exactly the same. Very badly drawn there. And we have their O. And in this case, we're going to add the hydrogens in to where we made a single bond. So I'll make them kind of red so we can know where they ended up. Hydrogen, again, just going to put back onto the oxygen. You probably wouldn't necessarily draw the hydrogen, but that is where the second hydrogen went, since it's line structure to that carbon there. And obviously we went from our ketone back to our secondary alcohol in this case, right? Which is 1, 2, 3, 4, 5, 6, 7. for heptanol, right? Would be our alcohol. And again, that would be obviously our reduction reaction. Any questions on that there? Question on alcohol reaction. Fun with reactions. All right. So a little bit more on this as we were talking about here. Methanol, also known as methyl alcohol. Again, you can see here, primary alcohol gets us to our aldehyde, one more oxidation, just popping our oxygen in there to make methanoic acid or formic acid from formaldehyde, which is methanol. Ethanol, obviously, as we just talked about, sort of our alcohol, and again, oxidizing to a aldehyde, and it can be oxidized down there to CO2 and water. And that is what you get from carboxylic acid that basically decomposes into CO2 and water is basically where that comes from. All right, so let's talk a little bit about thiols. And thiols is another functional group, and it is a sulfur-containing group. And it has a functional group of SH, so similar to OH. By the way, when we talk about OH and alcohols, actually, before we get too far here, when we talk about alcohols and our OH, and we touched upon it a minute ago or earlier on in terms of solubility with water, because it does have that OH group. Typically, alcohols are soluble in water. So if you had something like methanol, that would be soluble in water because, again, it has that ability, as I mentioned, to hydrogen bond. Again, polar group, and they could hydrogen bond. So we do see alcohols being very soluble in water. Up to about 5-ish carbons. So solubility does start to kind of drop off when you have a bigger amount of non-polar. So instead of this guy, if we had kind of like the one we had previously, let's draw a line structure, just like an OH, right? So what we have in this particular case is this part of the molecule, that's all carbons and hydrogens. That is non-polar all day. And it's very, very big. And now what we have here is just this very small polar part to this molecule. And what happens is that really big non-polar part gets in the way. It's called steric hindrance. It basically just gets in the way of things working nice with each other. Water molecules have a hard time getting in there and interacting well with it. You got this big non-polar part just kind of sticking out, not interacting well with water. Because that non-polar part will not react well with water, it gets in the way, and it's pretty much no solubility in terms of this alcohol with water. So kind of the magic numbers like that 4-ish to 5-ish and below, you're going to be pretty soluble in water with an alcohol because of that OH group. But once you kind of go kind of 5 and above, you will start to see the solubility with water decrease a lot. The opposite of that is what we saw earlier. We're looking at like glycerol and stuff like that. If you actually have a lot more OH groups on something, it actually will, again, increase the solubility of it in water, because everywhere there's an OH group, it allows it to interact again with water. The other effect that alcohols have is it is kind of the winner in terms of boiling points. Boiling points and melting points. Alcohols have high boiling points and melting points, and that's because of its ability to hydrogen bond with itself. So if you have something like methanol, it can hydrogen bond with another methanol, which is a pretty strong interaction. Again, between the negative side of one and the positive side of another. So because it has the ability to hydrogen bond, you typically will find alcohols with higher boiling points and melting points than things like alkanes, alkenes, and alkynes, which are essentially just all carbons and hydrogen and non-polar. remember things as we talked about that are sort of nonpolar like that are using dispersion forces, which are these really weak interactions. So they're not held together very strongly, as we talked about earlier. Things like methane, propane, butane, they're typically gases because they're not held together really tightly. But because the alcohol does have this OH group, it actually will have a higher boiling point than those guys, again, because of its ability to hydrogen bond, which is a really strong intermolecular force. Because it's a strong intermolecular force, it holds itself together pretty tightly, which means you need a lot of energy to separate those guys out. And that in turn means you need a higher boiling point for it to sort of go into the gas phase and stuff like that. So that's an important sort of property there of alcohols. They're sort of the winner. There's, as we will see, there's actually only kind of one thing that can beat them in terms of boiling points and melting points, and that's something that's got a couple other groups attached to it, but it's pretty much up there. So it's almost a safe bet if you're asked which one should have the highest boiling point, go with the alcohol, but there's only one thing that can kind of beat it in terms of that. All right, so back to thiols, which has a sulfur-containing group and a skunk on the picture, which is not a good smelling thing, I imagine. So because it does have sulfur, definitely does not have a great smell. And they also put that in gas, so you can actually smell it if there is a gas leak. Naming thiols, we're not going to actually name thiols, so you will not be responsible to name thiols. But as you can see down there, typically one way you can name it is just find the longest carbon chain and just add thiol to the end of it. So if you have one carbon, it's methane thiol, two carbons, it's ethane thiol, and so forth. But you will not have to worry about naming thiols, so that's good. So you still don't have to worry about that. But one thing you do have to worry about, obviously, for thiols is what the functional group is. And it does make an important sort of reaction we're going to talk about, and it does make an oxidation and reduction reaction that occurs. So if you take two thiols, doesn't really matter what they look like. So we'll just do something maybe, we'll do something like this. And I put it with another thiol, just make a smaller one. It can go through an oxidation reaction. And this oxidation reaction is similar to the oxidation reaction we were just talking about with alcohols. In those reactions, right, we pretty much remove H2. And the same thing happens with these guys. We're going to get rid of H2. And in this particular case, where we're going to remove the H2 is one hydrogen from the sulfur on one compound and one from the other. So that is where our H2 is going to come from. And I'll just kind of make it here. And that's going to be our H2. Now, what happens at that point is, frankly, you just take the H2 out and just squish them together, basically. So you're just going to push them together. And so I'll come over here underneath, kind of draw an arrow this way. You're just going to start on the left there and just copy exactly what's there. And the connection when you do this is always a sulfur to sulfur connection. So that is the connection that always occurs. And we will do that, yeah. We'll do our H2 over here. And this makes a bond here. And this is always, again, like I said, the connection between two sulfurs or thiols. This is what is known as a disulfide bond or disulfide bridge. So disulfide bond or bridge is kind of important with amino acids. There's cysteine that has that group in it. It will make that, and it's important in some proteins and stuff like that. But that is the oxidation reaction to thiols. As you can see, the way I kind of drew it, sometimes it's helpful just to back the two kind of SH groups onto each other. That way you can just visualize taking the H's out, and then all you have to do is just squish them together, basically using the sulfur as the connection point. So obviously, as we know, if there is a oxidation reaction, there should also be a reduction reaction that could occur. So if you started with sort of a disulfide bond here, and you added hydrogen, you will do the reduction reaction, which is we're basically just going to put the hydrogen back on. Now, clearly, if we connect these two at the sulfurs, where we put them back on is we break them back apart from the sulfurs. And basically, you get this guy here on the left. And you get this guy on the right. And basically, all you have to do is just pop a hydrogen on each of them there. And now you have basically your thiols back. Yeah. So oxidation, remove the hydrogen, squish everybody together, connect sulfur to sulfur. If you add hydrogen and you got two sulfurs connected, just break the sulfurs, give each one a hydrogen. Everybody kind of stays with each other. Questions on those two. So for thiols, you again need to know the functional group. You do not need to know how to name them, but you do need to know these two reactions. Yeah. Questions? All right, the next group we're going to talk about are ethers. And ethers have a functional group of basically carbon, oxygen, carbon. So ethers are carbon, oxygen, carbon. So that is the functional group there of ethers. They also have a bent structure like alcohols. So if you kind of draw in your lone pairs here, there would be some lone pairs. That guy right there is 4 electron pairs and 2 bonds, and that's going to give you your bent or V-shaped geometry. So it's very similar to the OH sort of group or what we see in water. There are different ways to name ethers, but I believe your book goes with this, so we will go with it. They use more of a common name sort of approach instead of the IUPAC name, so we will go with that as well. So common naming of ethers is not too bad. You basically just look at the oxygen in the middle of the functional group. And then you basically just identify the groups that are on the left and the right, and you put them in alphabetical order. In this particular case, there is a methyl group here and a methyl group here. So when we have two of the same group, we use the prefix. So this is going to be dimethyl ether. And you basically just put ether at the end. If you have different groups, obviously you go alphabetical and then just put ether at the end. So you had something like that. So if I had something like this would be called, take a moment there. All right, so first off, right, if I look at it, remember we have a carbon, and a carbon, and that right there is my ether group. That is a carbon, oxygen, carbon, right? So right there is the ether group. So if we're going to name it sort of our common way here, we're going to kind of go back and just focus in on the oxygen without erasing the whole thing, maybe. Or not. Oh, I don't want to do that. All right. So we'll just kind of redraw it here. Boom. All right, so we're going to focus in on this oxygen. And obviously here, if I go to the right-hand side, I actually only have a 1 carbon group. And if I go to the left-hand side, I have a 2 carbon group. So obviously my 1 carbon group is my methyl group. And my 2 carbon group, which is 1 and 2 carbons and only 1 there. That is my ethyl group. So again, alphabetical here. This would be ethyl, methyl, and ether. So ethyl, methyl, ether. Let's get any questions on that one there. Yeah. We don't. So this is a common name. So the real way of naming it is a little bit different. The IUPAC way of naming it, you actually you actually go with the longest carbon on either side. So in this case, this would be ethane, right? And this methyl becomes methoxy, and this is known as methoxy ethane is the IUPAC way of naming it. So, and they actually still don't use too many numbers with it and stuff like that. So you don't need numbers because it's implied that those groups are connected to the oxygen. Yeah. Other questions? All right. So as we can see here, we go to our oxygen. To the left, we have a methyl group. We have a propyl group. Again, alphabetical in this case, we would go methyl, propyl, ether. Ethers are used obviously as an anesthetic and to keep you hopefully not feeling so much pain. So in the 50s or so, they developed some other ones where they replaced a lot of the hydrogens with some fluorines, which made it a little bit more not as flammable and volatile to use. So they replaced some of those and had some better, I guess, less side effects as well. All right, so to finish up here, I want you. Okay, so since we're getting down, let's take a look here. Let's see. So again, 3 pentanol. We could just start with our 5 carbons, 3, 4, and 5. OL tells us it's an alcohol, and 3 tells us that is where it's located. So I'm going to go left to right. In this case, it really doesn't matter which way you go. You'll end up with your OH there. And we're just going to fill in our, again, appropriate numbers of hydrogens to give us our condensed formula. And obviously, 1, 2, 3, 4, and 5. And a little OH there would give us our line structure in this case. Any questions on that one there? Ethanol, that is just 2. And in this case, you could put it on either one, as you don't really have a number, and it's the same thing regardless of which carbon you put it on. So it looks something like that. And diethyl ether. So what I know about an ether is there should be an oxygen in the middle and carbons on either side. So when drawing these, that's sort of what I would start with and just think about the groups. So diethyl means there's an ethyl group on each side. That's a 2 carbon group. And I would just add those in kind of like normal. And now there's nothing left but hydrogens at this point, and we could go 3 there, 2 there, 2 there, and 3 there. Even if you're doing line structure, I'd kind of do the same thing. Start with the oxygen and do 2 carbons and 2 carbons, right? And you got kind of like a spider or whatever that may be, right? Walking there. Any questions on those there? Now here again, an ether is the carbon, oxygen, carbon. So again, I'm going to start with my oxygen in the middle. Ethyl again is a 2 carbon group. It doesn't really matter which side you put it on. So I'll just put it over here to the right. So we'll go with 2 carbons. Pentyl is a 5 carbon group. So 2, 3, 4, 5. Try to squeeze it in there. And now we're just going to put our hydrogens in. Didn't leave a lot of room there for this guy. Maybe squeeze them in. There are 3 there. And again, if you're going to do lines, same thing. We'll just go here, 2 carbons and 5. 1, 2, 1, 2, 3, 4, and 5. You have something that looks like that. Yeah. Any questions on that one there? Lastly, here, 2-chlorocyclobutanol, alcohol OL, 4 carbons, ring structure, right? Cyclo. So that looks sort of like a square, I suppose. And again, you could put the OH on any of those carbons you like. So I'm just going to put my OH there. And you also, again, have an option left or right here. So I'll put my chloral here in this case. Yeah. Any questions on that there? All right, well, later.